questions about this project. First, it's a project, it's got a problem you present. You want to get,
That's me, sorry.
you want to get, say, I don't know, 2.45 gigahertz Wi-Fi signal from here to Sanford Hall or your apartment. Problem is, the signal's too weak without some amplification, something like this. Here's the method I'm going to solve. You lay out the steps, go through, show the numerical simulations that validate it, or maybe don't validate it, and then go through the process. But I'm not looking for, well, I want to just plot constants versus frequency, or plot. I mean, that can be part of it. If you're investigating what would be the best way to link a signal, you could write an overall equation and say that this represents the power linkage, and then maximize that. You can plot it or do it, something like that. But I'm not looking for just a replication of plots or something like that. Y'all follow me on this, class? Now, the reason I'm telling you that is that's what they're looking for. They don't want something they can look up in a book. They want something that's kind of unique, something you come up with that's related to your own personal interest. And I don't like this, by the way. I'd much rather prefer I give each one of you an individual project, whether you like it or not, do it. But that's the statement I got, so I have to abide by it. Okay, clear on that? I prefer you use MATLAB or Octave if you're going to do any programming. I don't think people are going to be like you doing Python, but if you're going to do Python, see me. I really don't mind it that much. I'm learning it. Python's different enough that you have to download a lot of toolboxes. I don't know if you've done this. Anybody use Python in here? Well, if you do, and everybody does in the real world, because there's no formatting required to do data analysis. So you can just strip out stuff without doing anything. You can do all sorts of data mining. That's what people like. Well, the problem is you've got to download all these, I call them toolboxes, but they're really programs associated with what you want to accomplish. And I'm not really fond of that. Now, there's probably some site where you can download them all, I know. But I don't know that yet, so I don't particularly like to spend a lot of time searching for something that I don't know exists. Now, I gave you some homework, I got some questions. Basically, what am I doing? How are you doing what you're doing? I try to put the solution up for the first problem. Did y'all see that? I'm not asking you to do Fourier coefficients. I'm sorry that problem, I'm not gonna ask that. But you have to appreciate how we do real EMC, because in the real world, some of you, especially those in defense contract, are going to be doing the very thing we're doing here. And I thought I had a cold and stuff, so I went and got another COVID test. I don't know if it's my third, fourth, or fifth, and it was negative, so just to tell you. I did what I was, yeah, I know you were sweating. I was too. I kind of know the answer, but you have to do this, because at some point they're going to ask you, when you were sick, did you get tested before you exposed the students? And, you know, my luck, it'll be a lie detector test. Anybody here ever have a lie detector? Okay.
Have you?
No, I haven't.
They are not.
You didn't have to do when you were contracting? No?
I was classified long ago. I got security clearance. I don't have a top. Right.
Okay.
When I got my security clearances when I was in the Navy doing all that stuff, they do these interviews. And they interview everybody you know, and then they finally interview you and ask you things that they know from other people about you to see how you respond. And that was long ago. It was very interesting. It was before Facebook and all that. Yeah.
Like, I've done one polygraph and it's not comfortable. I didn't like it at all. They put you in a room by
My
yourself.
cousin worked for the CIA, and she was way up there, and she got lie detector tests all the time. She told me, I'm paraphrasing, you can't beat them, so don't even think about it. Put a thumbtack under your toe and do it. They know that. You're not going to beat them. Basically, tell the truth, and if they don't like it, so be it. All right, first, questions about the homework. Now, please, guys, on Monday, you're getting a quiz about this, so I can't be more clear about the urgency of the matter. If you don't understand something, this is the time to ask, okay? So I want to start with the first one. What is that? 3.1?
3.21.
3.2.1. For this problem, they give you the parameters about this waveform. It's the source waveform. So they give you this. And for this one versus time, they tell you that the peak value is 5 volts. That would be, I would call it A, it doesn't matter, all right? The second thing they tell you is the period of this, T. Well, they don't really tell you that. They say the fundamental frequency is 10 gigahertz, right? I'm sorry, wasn't it 10 gig or is it 5 gig? 10? They are megahertz, not gig. Sorry, megahertz, right? Sorry about that. Megahertz. Yeah, 10 gigahertz, that would be tricky. What are your clock speeds in computers nowadays? 1, 1.5, 2? Gig? Anybody know the high clock speeds? They're not 10, I'll tell you that. If they were 10, there'd be a whole lot more problems that I'd be being paid to solve. Anyway, they're at 10 megahertz, and that means the period is 1 over F naught, or it's 10 to the minus. See, this is 10 to the 7th hertz, so 1 over that is 10 to the minus 7th seconds. Everybody follow me on that, class? Now, once we have that, the other thing they tell you is the duty cycle, or duty time, is 1/2 or 50%, and that means tau over T is equal to 1/2, or simply put, tau is capital T over 2 or 0.5 times T, and that's simply going to be 5 times 10 to the minus 8th seconds. If you want to put it in terms of nanoseconds, you can. You all follow me how I'm getting these values? They give you the duty cycle is 50%, I believe, right?
Yes, sir.
Some people don't like that. 100% duty time means there is no pulse. It's just DC. Y'all follow me? There's nothing but DC. When they say it's 50%, it means this ratio to the actual time T, which is this, will be 0.5 or 1/2. That's all it means. After that, they give you a few other things. They give you the rise time. This is the critical. Now, tau rise, we always assume is going to be set equal by definition of T fall. And if T fall just happened to be faster, which it never is, than T rise, then we use the fall time. We use whatever is smaller, got me? Always that. And that was equal to, I think, 20 nanoseconds, is that right?
Yes, sir.
All right, now at that point, forget about the circuit and everything like that. Now the thing you take a look at is what does this spectrum look like in dB microvolts? Y'all follow my thoughts on this? So we know first of all, I'm not going to put the coefficients down in mathematics. I went through that. What the spectrum itself will look like, and this is F, and this would be a logarithmic plot this way. And on this axis, it's going to be 20 times the log of the voltage spectrum, Vs, over 10 to the minus 6. So this plot here would be in dB microvolts. Do y'all follow me? Right? How many understand what I'm talking about here? Okay, does anybody have a question or an uncertainty? I want to make sure I clarify everything. I'm just showing you the axes. And we're going to start, now remember the way that I did that waveform, right? I tore it up, and the first thing you got when you tore it up was here is that DC, or low frequency part, calling DC the low frequency. That was 20 times the log of simply what? A, the magnitude, times tau over T, the duty cycle, right? It's going to be that. And times 2, actually, because this is the cosine series. Do y'all remember when I took the exponential series and I turned it into a cosine series? There was the 2 magnitude of Cn. Y'all with me? So these are the coefficients of the cosine series, but it's just the envelope of that.
Is that
Now,
tau over T?
Yeah, it's the duty cycle. I'm putting it down there especially because he's recording this, and if you're viewing this, I want to make sure they see that this really is the duty cycle. Maybe I should blow that up a little. I'll put it the way it appears a lot of times. 2 times A is just the voltage level, which is 5 volts, of the square, or of that trapezoidal wave. And then it's duty cycle. Or duty time, whatever they call it. And then this is all divided by 10 to the minus 6. So it would be in dB microvolts. Y'all with me? We'll do this in a second. I just want to get everything down. Everybody clear? Did you have a question?
Yes, sir. Why did we, this might be a silly question, honestly, but why did we decide that it's gonna be microvolts?
dB microvolts is the way it's always done because
Okay.
anytime, just let me tell you about dB. You know what the term dynamic range means? Dynamic range, if you have 1 volt minimum, 10 volts maximum, that's a dynamic range of 10. 1 volt minimum, 100 volt maximum, that's a dynamic range of 100. 1 volt minimum, million volt maximum, that's 1,000,000. Now, the problem is with dynamic ranges, if you're gonna have signals that will have an appreciable portion all through that dynamic range, when you're talking about volts versus hundreds of thousands of volts, they basically can't be extracted. You can't see them. By taking the log of that, now I see the fine changes if it's logarithmic. It exposes orders and orders of magnitude of change. So dynamic range becomes visible. You can see the signatures of the signal at both high and low. That's the real reason for it. All right. So we do dB microvolts because most of the time in EMC analysis and in the real world, you're not dealing with hundreds of volts. You're dealing with millivolts, microvolts, nanovolts, and that way this scales things accordingly. That's the only real reason for this. dB microvolts is a standard. Have you got this in any of your other classes? dBm, dB microvolts?
dBm, yes, dB microvolts, no.
You didn't get, I say, and I'm not familiar with what your labs expose you to, but this is very common anytime you're doing work in the frequency domain for any type of antenna, Wi-Fi, or you might say high frequency circuitry. It's just standard to do it this way. Now, so this is gonna have a value. Then I told you before, the first cut frequency, I call it the F low, will be at 1 over pi, and this is just tau, right? That's the first frequency, and you have to calculate that. You get tau always by knowing what T is, and T is 1 over F, right? So now you have that, and this falls off at minus 20 dB per decade. Now you remember that plot I was talking about why these things occur, but the key thing is knowing that's the frequency. The next frequency that's important is right here, and that's at 1 over pi tau rise. And this is the high, I like to call this the high frequency cut. And then after that point, it starts going down at minus 40 dB per decade. Now we did this last time. Y'all follow me? So again, this is a source signal. Finally, if you wanted the value of the signal at any given frequency, if it was down here, this is the envelope. It's just a constant value if the frequency is down here. If the frequency is between here and here, then you would start there, right? And then, let me just tell you what it would be. If I want the signal Vs in dB microvolts, it's equal to 20 times the log of the magnitude of 2a, I'll call it tau over t, divided by 10 to the minus 6. And this is true for f less than f low. That's it. Does this make sense? That's down here, right? Here's the low frequency cut. Y'all with me? Now, if the frequency right there is greater than f low, but less than f high, then it's equal to 20 times the log of 2a tau over t over 10 to the minus 6, but then you have to take minus, move that, minus 20 times the log here, and this would be of f over f low And this would be for F greater than F low, less than F high. Y'all follow me on this, class? Because it's falling at a rate of 20 dB per decade, this will tell you, the log of this will tell you the actual weight on that. If it was 1 decade, if F was 10 F low, then this would be log of 10 or 1, it would be minus 20, so 20 dB per decade. Y'all follow me? That's true, and this would be VS and dB microvolts in that range. Finally, now we're going to go when F is greater than F high, and then it's going to be equal to 20 times the log of the magnitude of 2A tau over T over 10 to the minus 6 minus 20 times the log here of F high over F low, and then minus 40 times the log here, and it would be of F over F high. This would be if you're at F greater than F high. Does it make sense what I'm doing here, class? I'm just showing you how to calculate the value of this voltage in dB microvolts at any given frequency possible. Okay? Usually you're out here. That's the troublesome thing. I always worry about that. Now, if you think about this, they ask the value of the signal, and I'll draw the circuit, at the 11th harmonic. Is everybody familiar with the term harmonic? Whenever you talk about harmonics of something, it's some base frequency that's multiplied by an integer value. For instance, if you have a tuning fork, a C tuning fork, you hit it, it resonates at the frequency associated with middle C, and I don't even know what that is. You can call that F naught. If you talked about the first harmonic of that, it would be that F naught times 2. Do y'all follow me? Or it is, I should say, the second harmonic. The first harmonic would be F naught, second harmonic. Anybody here ever play musical instruments and stuff? You know how you have C down here, C, C, and the relationship, I forgot exactly if it's an order of magnitude or not, I have to look that up. But the basis basic thing with harmonics is they're just multiples, integer multiples of the fundamental frequency. That's all it is. Now when you do, especially when you do work where there's a lot of inductance and capacitance in the system, y'all know what the resonant frequency is. The basic resonant frequency is 1 over 2 pi square root of LC for a standard LC circuit, right? Regardless of where the resistance is. Well, there are other resonances that occur in systems that have to do with other values of L and C, but they usually have harmonics of the base frequency. I'm not going to go there because it would get a little confusing. Just realize that's what, when they talk about harmonic, it's always the integer value of the base frequency. I mean, with the fundamental, okay? All right, so now, here's the circuit they give you. They have a square wave here, and this is Vs, and then they have a resistance R equal 100 ohms. This is a very basic circuit. And then they have like 70 picofarads of capacitance associated with the input to an FET. Do y'all see that? Now y'all know an FET, a field effect transistor that's using, that grows an oxide, the standard ones. That's a capacitor, right? No DC current can really penetrate that. Y'all familiar? You've had this, right? Everybody had MOSFETs in here? Mm-hmm. All right, metal oxide semiconductor. They grow the oxide, right? They put metal down here. And when they want to have any kind of a change in transconductance here, they put a voltage on here that will pull up a channel, right? And then more current can flow. The whole basis for transistors that are using FETs is basically the input automatically has a capacitor block on it. Unlike when you use standard NPN or PNP transistors, you have to apply a capacitor in front of that if you want to block DC. Y'all with me on this, guys? So with metal oxide semiconductors, there's a gate capacitance that is not a function of frequency factor. And that'll be about 70 picofarads. And then they had 20 picofarads in parallel with it. I think it was 70 and 20. But anyway, the net result was this. They were in parallel. The net result is a capacitor equal to, or was it 50 and 20?
50 and 20.
All right, so I'm sorry, the net result is 70 picofarad total right here. And this is the output voltage, right? Make sure you all see this. This is the problem. Now, they want to know, here's the question, that's the signal here, source signal that we analyze. They want to know the value of the voltage here in dB microvolts for the 11th harmonic. That's the problem. And this is a very reasonable thing to ask. This is something I could easily see being asked in a real world situation. So I'm going to erase that and just work right here. You know the waveform. So let's do it this way. If I take a look at this circuit right here, right, and I want this output voltage with relationship to Vs, please just watch this. When I talk about V out over Vs, I use the term transfer function. That's very common in my world. I think it's true otherwise, right? Don't they talk about a transfer function as the relationship in the frequency domain usually of the output to the input? And here the way you get it, this is voltage division. So if you have two elements that are in series, and you want the voltage here, you would normally take Vs, or the input voltage, then you would multiply it by this impedance over this impedance plus this impedance. Do you all agree? And since I wanted a transfer function, I wanted the ratio of those two. Vs is divided out, and here I get the impedance there, which is 1 over j omega c over that one plus r. I'm just doing it so everybody can see it clearly. I don't want to leave anything to chance here. You all agree? Now don't use that formula. Try to make it as easy to deal with as possible. So multiply top and bottom by j omega c. Then you get 1 over 1 plus j omega r times c. You good with that? It's probably the COVIDs. You ever seen? I know. Anyway, I come down to here, and I want you to just watch this one part. Believe it or not, this sometimes causes people problems. When I look at V out, it's equal to this, and I'm just going to call this H of omega. It's just that, it's H times Vs, right? H of omega times Vs. I'll try to make this as easy to understand as possible. Do you all agree with me, first of all? Now, I want this in dB microvolts. So 20 times the log of the magnitude of V out over 10 to the minus 6 is equal to 20 times the log of the magnitude of Vs times H of omega over 10 to the minus 6. The only thing I'm doing here is literally just cut and pasting the definition above for V out. Y'all with me? Now y'all know that log AB is log of A plus log of B, right? I can do this as log base 10. So what I'm going to do is say this is really equal to 20 times the log of the magnitude of Vs over 10 to the minus 6, right? And then it's going to be plus 20 times the log of the magnitude of H of omega. Y'all agree with that? This is like A, this is like B. Follow me? I just separated. Y'all with me? And the 20's out in front of both. Correct, class? It's a multiplier. Believe it or not, this is where people, and they're afraid to ask questions about it. They feel they should know it. But I'm trying to be as clear about this as I can. Do you all see this, class? Now, why did I do that? Because this we're gonna get from that. Alright, we're gonna get, and this is gonna be 20 times the log of that transfer function evaluated at the frequency of interest, or the 11th harmonic, okay? Everybody understand the thoughts? So, next question, I know my fundamental frequency here is equal to 10 to the 7th hertz, right? They want the 11th harmonic. That's simply gonna be F11 is 11 times F naught, or it's what? Really, 110 megahertz, if you wanna do it with megahertz. Did you all agree with that, class? That's 11 times 10 to the 7th. Do y'all agree? Now, that means when I come down here and evaluate this function h of omega, what I really want is h of 2 pi times, and this is what omega be, times 110 megahertz, right? Really, I want the magnitude of that. Do you all follow me on this, class? Okay, and what is that gonna be? Well, the magnitude of this is just going to be, I look there, it's 1 over 1 plus j, omega here is 2 pi, right? F is 11, or 110, and you can put times 10 to the 6th, and I want the magnitude of that, so if I, or times r times c, pardon me. This is times r times c right here. And I want the magnitude of this, so that's 1 over square root of 1 plus quantity 2 pi times 11 times 10 to the 7th. I'm going to do it this way. Square it times r times c squared, square root of that. And somebody can give that to me, if you know the method I'm using, right? I'm just taking the magnitude of a real and imaginary part. Follow me? Omega would be 11 times omega naught, and omega naught would be 2 pi f naught. How many see this right here? Okay. Anybody, are you with me, everybody? All right, what is that? Can you just give me the value?
What is pico? Is it 10 to the negative 12?
Yeah.
Okay.
Nano is 10 to the minus 9.
Okay.
You get into femto, you know femto? Minus 15. Anything below minus 15 I don't work with normally. But
I got 0.202. I don't know.
anybody have a scientific time like E for something? What do you have?
0.202.
0.202 for that? Is that right? I don't know, is it?
I can do it again really quick.
Yes.
Okay, thank you. We'll go with that. So, when you take a look at the value here, first we gotta get this at 111 megahertz, right? So let's see where these values are. We did this part of this last time. Isn't this like 6.3 something megahertz for this one? Can you give that to me, this frequency? It was a homework problem. I assume some people took a shot at it. Oh, I just need this value. Went over pi tau, and tau is,
It's 6.366 times 10 to the 6th.
Thank you. So this is 6.366 megahertz, right? And what's this one, 15.9?
Yeah, 1.59 times 10 to the 7th.
15.9 megahertz. Agreed? Now, we know that where we want to evaluate this is the 11th harmonic, or it would be 110 megahertz, correct, class? Are y'all with me? So 110 megahertz is way out here, right? Obviously, we're at a frequency greater than the high frequency. Clear on? So I'm going to evaluate first the source voltage in dB microvolts there. I'm running out of room. I'm going to get rid of this log AB business. Now, and take a look at this. So now I'm gonna have this term right here, which is the source voltage in dB microvolts at that frequency, would be 20 times the log, right here, and it is 5, right? Because this is gonna be 1/2, so this is A over 10 to the minus 6, so it'd be A is 5. 5 over 10 to the minus 6, right? Then we're gonna have minus 20 times the log of FH over F low, and that's 15.9 over 6.36. The megahertz cancel. And then, you keep going, now we're also gonna take what? This takes care of the DC term. This is between the low and high frequency, right, the fall off. Now we have to do what? Add one more thing, minus 40 times the log of the final frequency, which is 110 megahertz, over the upper, which was 15.9 megahertz. Do y'all agree with that? And we did something like this last time. I'm just applying it now to a problem. Y'all with me? What do you get for this, guys?
92.4.
I'll put this V source dB microvolts. Go, say it again.
92.4.
92.4 dB microvolts at the source, and this is at the 11th harmonic. Y'all agree? Can y'all see info in the back? Okay. That goes right here, right? So now to replace that, now I say the actual V out right here in dB microvolts would be equal to that value, 92.4 dB microvolts, minus, or plus actually, 20 times the log of 0.202. And can you give me that?
78.563.
Thank you. dB microvolts. Now, I got something to say about this. This, whenever you're doing EMC analysis, you always are trying to do, anytime you're doing EMI, radar design, you always want the worst case possible problem that can happen. So this is the envelope of the peaks. Y'all follow me on this? The value of that signal could be less than that, but if it's less, we're happy. We would prefer it was non-existent, because we're looking at things you don't want. All these harmonic components, you don't want them. You would ideally like just the low frequency signal, nothing else. But the the components that are harmonics, are the fundamental, they're the thing that irritate everybody in the real world. They cause all sorts of problems. So this is the worst case. Now the actual value in the problem, if you use the actual coefficients in there, the C of n that I define, and you multiply it by 2, take the mean, it would be less than this a little bit. I think it's 73 point something, or in the book 73.5. That's only a couple dB, 3 or 4. I mean, percentage-wise, it's a small percent, 1 to 3% difference, but thing is, it's less. So this is worst case, and you always go for worst case when you're doing any kind of an analysis of failure or a bad effects. And EMC is always a bad effect. You don't never want it, never, unless you're trying to jam the enemy. Okay? Y'all with me on that problem? Yeah.
I got kind of lost at the end. Why do you just plug the 92.4 in for the 20 log VS over 10?
You see this right here? That is what we're doing right here. This is the source itself, the spectrum of the source, right? Well, when we take, first you have to agree with me that V out is H of omega times Vs, right? Now, if I want V out in dB microvolts, I take 20 times the log of V out over 10 to the minus 6. Well, that's 20 times the log of, and I just plug in the V out is Vs times H over 10 to the minus 6, right? Now look, this first part, Vs over 10 to the minus 6, that's like an A, log AB. Log of A I break out times 20, plus 20 times log of the transfer function's value. That's how I got that. So this right here, the 92.4, is this value. It's the source It's the value of the source voltage spectral component in dB microvolts at the 11th harmonic.
Okay.
But that's this. I don't want that, I want this, so now I have to take into account the effects of that transfer function.
So there's a difference in VS and then VS dB microvolts?
Well, VS, usually, when you've been doing lab, it was in volts, right? VS here is dB microvolts, so this is a big difference.
Okay.
Out of curiosity, and this is a typical thing somebody asks at some point usually, just to see if you know what you're doing, if you're doing EMC analysis. They'll say, all right, I got this. What's the actual voltage there? In volts, not dB microvolts. How would I get that? It's a reasonable question.
20 log X equals,
We always
That-
go to the fundamental formula that defines that, and that's why. You're right. 20 times the log of any voltage in dB or any voltage right there, over 10 to the minus
Wow.
6, is what? The voltage in dB microvolts, right? So if we wanted this, believe it or not, people mess this up on final exams. I asked this problem, this kind of a question, so they have to have an understanding what the units are. First, I'd take this and divide it by 20. So I'd have V dB microvolts over 20. That's equal to the log of the magnitude of V over 10 to the minus 6, right? I'm just showing you the plain truth. How do I go through the rest of the guys? Take everything to the 10 to that power, right? 10 to the power here versus there. So that means now I have V. If you knew how many people mess this up, you'd understand why I'm doing it. If you see it, you're wondering why I'm doing it. I'm at this point, I want V. So that would be V dB microvolts over 20, right? And take that whole thing to the power 10, that's V over 10 to the minus 6. Do you agree with that? Then I would have to multiply this by 10 to the minus 6 to get V. Out of curiosity, what is the value? We had V dB microvolts is what, 78.5 or something like that? So what is this? If that's 70, it's 10 to the minus 6 times 10 to the, what is it, 78? I'm going to put 78.5 over 20. And tell me what that is in volts. It's more than a microvolt, huh?
8.5 millivolts.
You get about 8.5 millivolts? That's not much. Not much. And I want you to think about something too. What's the range of the signals we're talking about? We've got, I think the low frequency value here, this right here, I want to say it's like 136, something like this, dB microvolts. That's for a 5 volt signal. It goes all the way down to 78.5. That's for an 8.5 millivolt signal. Now if we try to just plot that linearly, the scale on that, this thing's invisible, you can't tell, it's gone. Y'all with me, class? Because the difference between 0 volts and 8.5 volt millivolts, when you have a 5 volt mid scale, if it's linear, is impossible to see, just so everybody knows it. Okay, any other question about this one? I want to do it. I want to spend a lot of time just talking about this. We're going to do the next one and then the next one, kind of quick, okay? Y'all with me? Hope you're getting a handle on it. Let's do the next one. And you can see here why bandwidth kind of loses its meaning. Because there's things going on at every frequency, and bandwidth itself is sort of used for rule of thumb estimates, but it's not very good if you're doing precise EMC evaluation, or EMI, or radar, or okay, next problem. Does somebody have that in front of them? Down here. All right. Help me do this and that, okay?
all right.
he gives us the spectrum, basically a spectrum we just looked at. This is versus omega, isn't it?
Yes.
All right, and he doesn't put it versus F, but omega. And then he has, I want to say that, basically. All right, so what's this
It's at
value?
120 dB microvolts. And then
What's
it's
this point?
10 to the 6, and then 20 to the 6,
So this is 20,
times 10 to the 6.
6, and this would be omega I, all right? And this is minus 20 dB, right?
Yes.
And this is minus 40.
Yes.
Then over here,
It starts at negative 30 dB
okay, thank you.
and goes up at a positive 20.
Oh, one other thing too, this is the log of omega axis. And this will be log of omega.
And the origin is 10 to the 5 there.
All right, so they say the minimal frequency is 10 to the 5th. Omega is 10 to the 5th radians per second. And it's going up at 20 dB per decade? And is this H or what do they call it?
HJW. Yeah.
All
H
right.
and then X.
What he's really doing, this is not drawn very well, but I hope you can appreciate this. His system is this, he's calling this the spectrum of the input, but instead of V, he just says it's X of M. Doesn't matter if you call it X, voltage, doesn't matter. It's something associated with an input.
Dr. Baginski,
Uh-huh.
I think it should be minus 30 dB.
Oh, yes, where it starts on the.
Oh, is this minus 30 dB?
It is.
dB microvolts then, right?
No, it's just dB.
All right, minus 30, I'm sorry, 30 dB there, but this has got, yeah, this is dB microvolts. Okay. All right, so what he does, and thank you for, he's got a signal input X of omega, and here is my H of omega. And my output Y of omega is simply X of omega times H of omega. Now, y'all familiar with that standard block diagram approach, right? Input, output, it's multiplied. Y'all, you've seen this stuff. I know you've seen it in signals and systems. I think you've seen it block diagrams like that in circuits too. And how many had controls in here or having it? John Hung will show you this. Dr. Hung in controls. Probably saw it somewhere else. So what they want is this. With the information provided, this is a very reasonable question, they want to know what this is. Now here's the thing people will do, and they'll do it wrong because it's sort of a knee-jerk reaction. They'll say, I'll multiply this, by this, by this all the way through. The problem with that is those are logarithmic scales. So just watch. So if you took the output 20 times the log of magnitude of Y of omega, that's 20 times the log of X of omega, right? Plus 20 times the log of H of omega. Y'all agree with that? If you take the log of the product, you take the log of the first term plus the log of the second. 20 is a scalar multiplier out front. Now, I'm really trying to make sure you see this. I tell you the truth, people mess this up. And it always bothers me because they just have to be attentive to not mess it up. All right, what is this saying? If we have logarithmic scales, we just add. Y'all see that, class? You just add. So when we want the output, and this is versus omega or log of omega, of this, take a look. Here, I think this is 10 to the 5th too, isn't it?
It doesn't
It won't
specify.
matter, it's flat as far down as you go. Now here's the thing, you're gonna add these, right? I'm gonna start at 10 to the 5th here, omega equals 10 to the 5th. 10 to the 5th. get the first point, I take this, 120 dB microvolts, and I'm gonna subtract 30 from it. Do you all follow me? Everybody with me? Somebody said, but the units are different. A dB, and Riggs used to say this. By the way, Dr. Riggs is retiring next semester. He's not gonna be here. I just found out about it about a week and a half ago. I'm very sorry to hear that, because he's always fun to listen. Anyway, for this right here, it's this dB microvolts. You can add dB to it, all right? It's not a problem. The microvolt itself really isn't part of the equation. If you think about, we had the log of voltage in volts divided by 10 to the minus third volts. Volts is gone. Y'all follow me? The reason we put dB microvolts is to indicate what we normalize with. So when we do this, you can add them. So I take 120 minus 30, which is 90, right? So it comes in at 90. 90 dB microvolts. It's still dB microvolts. Now look, all the way up to 10 to the 6th, right? This is flat. Same value it had back here, right? Follow me? It's just one. But this keeps going up at 20 dB per decade. When I go from 10 to the 5th to 10 to the 6th, up here, I went 1 decade, haven't I? You know, it's just a straight line. It's got a slope of 20 dB per decade, and now it comes up here to be a value of 110 dB microvolts. And the slope is plus 20. Now, at that point, what happens? Just look at this and think to yourself. Here's where I'm at. Now, that is continuing to go up at a rate of 20 dB per decade, right? But what happens here? It's going down at 20 dB per decade, or the net effect is 0. There's no change. It's flat. You all see that, everyone? So it stays flat until what?
20 times 10 to the 6th.
Right here, right? And at 20 times 10 to the 6th, right? Now all of a sudden, this starts going at minus 40 dB per decade, right? Y'all with me on that? So that means now it's going down at minus 20 dB per decade, right? Because this is still going up at 20 dB, this is going down at 40 dB per decade. Net effect is minus 20 dB per decade. Y'all see that? What did the question specify they wanted?
Determine the magnitude of the output of the system
At what
at 50 times 10 to the 6th radius.
All right. Now, y'all listen, because I want to make sure we're clear. They want to know the value. This is the output. Y in dB microvolts. And they want to know the output here when it's 50 times 10 to the 6th, right? So how do you get that? Now this, I want you to just think for a second before I answer this. I want to make sure you give it some thought. Dr. Baginski wants this value to be worth 10 points on Monday. Think of that. How would you get that for 10 points? Well, do you know the value here? Yeah, what is it? 110, right? Correct? So to get the value here, I'll call it Y dB. Matter of fact, let me put it up here. To get Y in dB microvolts at omega is equal to 50 times 10 to the 6th. I take the value there, 110. And now, hear me now. Y'all with me? Now this is going down at 20 dB per decade. So I'm going to minus 20 times the log of what? Of the frequency I want the value at, which is 50, right? Y'all see this? 50 divided at the frequency it started going down at 20 dB per decade, right? And that's 20. Do y'all see this? And that's it. So can somebody give that to me and then we'll look up it? See, it's really, it's 110 minus 20 log of 2.5. Anybody?
102.
102 dB microvolts, is that what the answer is?
Yeah, we're on
But do you
2.04.
all see how I got it? Now here's a question I might ask on Monday. Here's a question I might ask on Monday, making sure that people wait. Suppose I ask you the voltage somewhere in here, the voltage somewhere in here. In other words, I give you a frequency and the voltage somewhere in here. Know how to get the voltage at every point. You all follow me on that? You know that, you're good. You know how to construct that based on, remember that curve I had, the gain curve and the input curve, okay? I think we're out of time, but I hope that answered your question. That's something I didn't do, I kind of thinking myself. I have, not that it matters, your projects, or sorry, your hand-in homework that everybody seemed to do extraordinarily well at.